Hello and welcome back to another exciting episode of a journey through the fascinating world of tensors. If you're just joining me, don't worry, you can catch up the part 1 and part 2 on my channel as I've put up the description and the details on the I button. Today we are diving even deeper into the foundation of tensors, exploring concepts that are essential for our understanding, exploring the concepts and exploring the powerful mathematical tool. Understanding the basis of vectors, transformations, coordinate changes are like mastering the alphabet of mathematics. It is the foundational knowledge that allows us to express complex ideas and solve real-world problems with precision. In this video, we are going to deep into learning few of the fundamental or core concepts of tensors, which would help us to do even complex mathematics in the world of tensor. My name is Shaunak and you're watching this video on my channel. Physics for Students, welcome to lesson 3 of Tensor Fundamentals, a beginner's journey. Well, before I go ahead and explain the details of today's video, here is a quick recap if you have missed on and just a brief idea on what I have covered in the last video. Well, the basic idea that I covered is that if we are measuring a vector in a flat space, then what we do is that these components ax and ay, these are the components of the vectors. Whereas if you put this same flat vector on a curved surface, this goes like this. We name the curved surface as x prime and y prime. And what happens is that the vector remains the same, but the components of the vectors, as you can see, a prime x and a prime y becomes longer. So the essence of the last videos, if I can summarize, is this. A prime x is longer, a prime y is longer, whereas a remains invariant. So the basic idea of developing tensors, mathematics of tensors, is to find out an exotic mathematical tools through which we can measure the vectors, whereas the vector would remain invariant, but the components would change. What would be the transformation laws? What would happen when we go from flat place to curved space? This was basically the idea of tensors, and you can check it on the I button. Part 1 and part 2 comprises more or less of this idea. Now we basically go back to this one also, where we see that if I rotate the coordinate here, as you can see, this ax and ay, this is the non-rotated system, and when I go into this part, that is a prime x and a prime y, which is the rotated from the left hand side, we see again this one is bigger, the a prime x is bigger and a prime y is shorter. So again, from a static frame of reference, we rotated into rotated frame of reference, and in this way we cited certain examples in the previous video. The basic essence again is to learn the tensors, to learn the transformation rules through which things will be easier to understand. Now this is basically a metric tensor, which is our target, which we learn is a kind of a complex mathematical tool which is used in differential geometry and further in Einstein's general relativity. So this is more or less what we learn by rotating the frame of reference or moving from a flat to curved space. The components of the vector changes, whereas the vector remains invariant. So we move on to today's video and we start with something very important. Now you see in the previous section what we have done is that what happens to the components of the vector when the two-dimensional Cartesian axis is rotated, and the results is quite surprising. This is the result. The components of the vector reference to the new rotated axis are different from the components vector to the original axis. Now, more specifically, what we can say is this one, that the new components are weighted linear combination of the original components. If you're wondering what is a weighted linear combination, go back to my second video on the tensor analysis. You will be able to find out what is exactly the weighted linear combination. So what we see is that the components of the vector reference to the new rotated is different from that, and the new components are basically the WLC, or the weighted linear combinations of the original components. Now here is an important point. As we go ahead in our studies in tensor analysis, you will see that we are dealing quite often with two concepts, which is called the covariant component of the vector and the contravariant component of the vector, which will essentially lead into a contravariant tensor and a covariant tensor. Now in these discussions, these words are very often used, and what we mean by covariant, I'm just giving a very basic idea. Mathematically I will explain in the further videos that components transform in the same way as the basis vectors. Now what do I mean by that? Co means with. So whatever the components which transform, it will transform along with the basis vector. Whereas contravariant component is something which will vary opposite way to the basis vectors. So now these things sometimes get very much confusing for students, so I would explain the mathematics later, but just let us understand that covariant is something that transforms in the same way as the basis vectors, and contravariant is something which happens in the opposite way of the basis vectors. Now you see here, before we go ahead and learn anything in tensors and in the vector part, what we need to understand is that what is called the basis of a vector. This is super important, this is very fundamental, and we need to first understand what is a basis vector, coming up in the next part of the video. What is a basis vector? I will give you a very simple example. Imagine a flat piece of paper, something like this, and you want to draw an arrow on it. So what I do is that I draw an arrow something like x and y axis similar. So you see the starting point of the arrow is where you put your pen on the paper and the arrows goes either in this, in the x or the y direction. Now for example, in a two-dimensional space, for example this one, which is typically a piece of paper, we typically use two arrows to determine our basis. So one arrows point to the right and another upwards. So these are the standard directions, and any other arrow in two-dimensional space can be created by combining these standard arrows. That means this one, I would say a reddish kind of this vector, if I want to add up that, okay, I want to add this vector, so I can do this one and this one. So if I name the vector as the big vector as A, and the components, that means part 1 and part 2 as A1 and A2, I can obviously say A equals to A1 plus A2. So you can see that these arrows in the two-dimensional space is basically created by combining these two standard arrows. So you can think this like a treasure map, whether you will go forward, upwards, in which direction, that is what the basis of the components, basis of the vector, it determines. Similarly, if I draw in this way, this arrow, and if I take this one and name this as C, then I can say C equals to C1 plus C2. So what in a plain easy language, what I can say that let us think of the basis vector as a special set of instruction that tells where you will go. Where will the arrow go? In this direction, up, left, right, etc. So you can say it is a rule book. It is a set of rules for drawing arrows on your paper. So now you think that the basis of a vector, as I told you, is a special set of instruction that tells us how to draw that arrow. Now the rule book consists of maybe 1 or 2 or 3 directions, doesn't matter, for moving upwards, right or left. Now you see I can go in this way, I can go in this way, either in this way. So what I can tell you is that the basis of a vector is like a kind of a guide. I can tell is that the basis vector is like a guide that helps you to understand how to create an arrow by telling which way and which direction to go. This guide is crucial when you're working with vectors in math and science, because it helps you to describe where things are and how they move in space. So here it is. Any other arrow in the two-dimensional space can be created by combining these two standard arrows. So the basis, that means what forms the building block or what forms the basic base. So you can understand from now on, it is a kind of an instruction, a set of rules, a set of guidelines which will help you to draw any other vectors based on the two basic vectors, which are either this way or that way. Now if I take a three-dimensional vector, even x, y and z, so I can say that this one describes in directions. These three directions will obviously give us a roadmap that any arrow in three-dimensional space can be combined. So if I take this, then I can add as A1, A plus, A2 plus A3, and then I can take this and this and this and then combine this. So what I can tell is that, for example, in a kind of a child's play, when we say that these are the building blocks, so what we can say that either one points to the right, one points upward, one points forward. So with these three standard directions, we can describe any arrow in three-dimensional space. So the basis of a vector is a space is like a set of instruction building blocks that allows us to represent any vector within that space. It is very fundamental, very important in mathematics, because it helps us to work with vectors and understand how in different dimensions things work out. Now this is what is called the basis of the vector, right? I hope things are quite clear. Now we will move to the next part. Now you see, the basis of a vector is a set of vectors that can be represented any other vector in that set. So what we can say, for example, the standard basis, if I take the naming convention in a two-dimensional space, is what? I hat and j hat. So we just put an hat on it. This hat means they are perpendiculars to each other and they have a magnitude of 1. So any other two-dimensional vector, as we have mentioned, that any other two-dimensional vector can be represented as a linear combination of I hat and j hat, obviously. So for example, I will show you a vector which is 3 and 2, and this can be represented as constructing a vector by adding 3 copies of I hat and 2 copies of j hat. This means what? That 3 and 2 can be constructed by adding 3 copies of I hat and 2 copies of j hat. As simple as that. So say for example 3 comma 2 equals to 3 into I plus 2 into j, and I and j, because they are magnitude 1, so it gives you back the result. So here it is in graph we say I as the x-axis and j as the y-axis, and if you take a three-dimensional space it will be I, j and k. That's it. Okay, so any vector which is residing on a kind of a plane surface or a 3D surface or a flat space or a paper, whatever, this is typically known as vector space. Now vector space has got many technical definitions, but I'm avoiding this for the purpose of this video. I'm just telling you that this is a vector space. So a basis of a vector of three-dimensional space is a vector that can be expressed as a linear combination of any other vectors. In other words, what we can say, I, j and k. So one common thing that we find in here is that this one. So I can be 1 0 0, j can be 0 1 0, and k can be 0 0 1. And in case of a two-dimensional thing, what we get is this one, 1 0 and 0 1. So this would be, I'm so sorry, this would be 0 1, right? So this would be 0 1. Now you see that what happens is that these vectors positive points in the positive x direction and y direction respectively, and another common basis of two-dimensional space in the orthogonal basis, which consists of these vectors. Okay, so if I take a vector, say for example 1, 2 and 3, say for example a 3-dimension for the purpose of I, j and k, so we can definitely do this kind of a linear combination. We can do this by representing each component of the vector as a linear combination of the basis vector, right? So 1, 2 and 3 can be represented 1, 1 0 0 plus 2 0 1 0 and 3 0 0 1. Right? So but note here that the basis vector must be linearly independent. So we take another vector 3 and 4 that can also be represented like this: 3 multiplied by 1 into 0 plus 4 multiplied by 0 into 1. But remember one thing, that the basis of the vector must be linearly independent. This means that no vector in the basis can be written as a linear combination of the other vectors. Don't worry, I will just tell you what is that. But before that, this part is quite clear, that how we are representing a 3-dimensional vector and 2-dimensional vector as a linear combinations. Now the question now rises that how can we represent, I mean to say, how can we show or represent the basis vector? Let us look into the next part of our video. So R2 somehow looks like this: 1 0 and 0 1. Okay, and this is actually the, I would say, the two basis vectors are linearly independent because no vectors can be formed as a linear combination of the other. So 3 4 can be only 3 multiplied 1 0 plus 4 multiplied by 0 1. Therefore what we can say is 1 0 and 0 1 is obviously a basis of R2, obviously, because this cannot be combined with any other combination. Similarly in R3 what we see is that 1 0 0 0 1 0 0 0 1, if we take 1 2 3, then 1 multiplied by this, 2 multiplied by this, and 3 multiplied by this. Therefore these sets can be obviously called as a basis of R3. So I hope this point is clear, because therefore this set 1 0 0 1, why it is called a basis of R2? Because no other combinations can be done. 0 1 1 0 0 0 1 0 0 0 1, why can be called as a basis of R3? Because no other sets can be formed, and it actually gives back the result. Okay, so what I was talking is about representing the basis of a vector, coming up in this part of the video. So as I told you, R2, it actually, the basis consists of two linearly independent vectors that span the entire space. Now the spanning of vectors, I think you have read it. It is basically the basics of vector. So if I take the most common choice for the basis vectors, these are actually named as this E1 10 and E2 01. This is basically E1 represents the x-axis, pointing in the x-axis, and E2 represents the y-axis. Now these two vectors are linearly independent because you cannot express any other as a scalar multiple of other. That means what? There is no way to find scalars such as A E1 plus B E2 so that the result is 0. That is not possible. So if I take any other vector, say for example V in R2, it can be represented as a linear combination of the basis vectors. How? Simple, like this. V equals to V1 E1 plus V2 E2, and here this one V1 and V2 are basically again the components of the vector V. As simple as that. These two V1 and V2, these are nothing but the components of the vector V. So V1 and V2 as it expresses the vector of this standard respective basis. Okay, let us see another example. Say, so this is one we have shown V equals to V1. Now suppose that we represent V equals to 3 2 using the standard basis. How we can do? Very simple. We can use this one, V equals to 3E1 and plus 2E2. And in this representation you see V1 equals to 3 and V2 equals to 2. What does it mean? It means that the V is a linear combination of 3 times the x-axis, obviously 3 times the x-axis unit vector and 2 times the y-axis unit vector. That's it. 3 times I take the x-axis unit vector and 2 times the y-axis, so it forms 3E1 plus 2E2. Now as far as this part of the video is concerned, I hope that things are clear, but when we deal with the representing of the basis vector, few important points comes right now. This is the point. Remember one, that every vector space has a basis, obviously. All bases for a given vector space should have the same number of vectors. This number is what is called the dimension. How much dimension is the vector space? And every vector, remember, in a vector space can be expressed as a linear combination of the basis vectors. This is super important. So every vector should have a basis. All bases should have same number of vectors. This number is called the dimension of the vector space, and every vector in a vector space is uniquely should have a linear combination of the basis vectors. Now here comes a question. We are talking of linear dependent vectors, linearly dependent vectors and linearly independent vectors. What do I mean by linearly dependent and linearly independent vector? Let us find in the next part of our video. What is linearly dependent and what is linearly independent? I will give some very basic examples, simple examples, so that things become clear. So here is a basic definition. A set of vectors is linearly independent when we call it can be written as a linear combination of the other vectors in the set. So let us not read the English part and let us go back directly to the mathematics. So if I see that the set of vectors 1 0 0 0 1 0, so it can be written both of row and column, right? It doesn't matter. Main thing is the concept. It is linearly independent because no vector in the set can be written as a linear combination of the other vectors. What do I mean by that? Let me show you an example. Suppose we get an equation like this: A1 0 0, B 0 1 0 and C 0 0 1, which is equals to 0 0 0. And here A, B and C, minded, these are scalars. Now if we expand the left hand side of the equation, we get this: A 0 0 0 plus B 0 B 0 plus 0 0 C equals to 0 0 0. And from here we get this equation. I will take this in the next page and I will show you what actually it is. So this gives us the linear equation as this. So what does it mean? That means that the only solution to this system, I mean to say trivial solution, will be what? A equals to B equals to C equals to 0. That means that no vector in this set 1 0 0, 0 1 0 and 0 0 1 can be written as a linear combination of the vectors in the set. Therefore it is called linearly independent vectors. So if I can not get anything from this set, no vector set in this set can be written as a linear combination of the vectors, then in what it is called linearly independent vectors. Question comes is what is called linearly dependent vectors. Let us see in the next part of our video. So if I say, for example, I take an example. Now I'm not going to tell those definitions because English definitions are quite confusing if I'm talking of mathematics. So a simple example I will take as 1 0 and 2 0. This is a linearly dependent vector. Can you tell me why? This is because the second vector, I would say the second vector can be written as a multiple of the first vector. That means 2 and 0 can be expressed as 2 multiplied by 1 into 0, which gives back to 0. So anything which will give back the next one is basically linearly dependent, and if it does not give back, it is linearly independent. So again, let us see this as an example: 1 1, 1 2 and 2 2. Again, this is a linearly dependent vector. Why? This is because the third vector can be written, as a summation of I would say first two vectors, 1 1 plus 1 2. So what we tell from here is this example. If I take another example, vector A equals to 2 1, then and vector B equals to 4 2, we can always say that vector B equals to 2 multiplied by vector A, obviously, because 2 multiplied by vector 2 multiplied 2 equals to 4 and 2 multiplied by 1 equals to 2. Now this actually brings you to this. So in other words, if you double the components of vector A, you get vector B, because one vector can be generated from other using simply by the multiplication. So if it generates anything and gives back the vector, this is linearly dependent, and if it does not gives back, it is a linearly independent vector. Okay, at this part of the video, I would like to draw your attention to one of my previous video, that is lesson 2, and I would like to show you something very important. Now you see, this was basically what I have done in the earlier video. Note the thing at the bottom is important. These are actually, I have shown that the components of the original unit vectors, that means from non-rotated coordinate system, I was going to express in the rotated coordinate system. This is important, number one. Second thing is that if you really have missed, I have given you this thumbnail, lesson number 2. This would give you the actual derivation and idea why this is important. Now also, I have talked in the last video that this can be represented as components of the same vector equal to inverse transformation multiplied by components of vector in original system. Now the question is that if I am asking this one, that how do you change a given vector into a different vector? That means the unit vector should be in a different coordinate system. What I am asking is this: how do you change a given vector? You see, the earlier one, let me go back, this was just the components of the original unit vectors which are in a non-rotated system expressed in a rotated coordinate system. Now my question is that how do you change a given vector into a different vector? Or I can say that original vectors, how they can be expressed in the new coordinate system. Or I can also say how to make a new vector using rotation. So this is coming up in this part of the video, that how to make a new vector using rotation. This is where we paused. Remember, in lesson 2, this is where we paused. And I told you that this is what I would be explaining you in the third video, and this is what I am doing right now. But before that, I just made the basics clear, that what is the basis of a vector and all those stuffs. Okay, so how do we make a new vector out of that? Now to understand this process, I would consider 3 figures, right? So first of all is this figure, this one. So you see that it considers of a vector A which points in this direction, and the rotation is shown over here, and this is known as vector A to point in a different direction, which means it is no longer the same vector, which is why it is labeled as A prime. Okay, now the relationship between the components of the original vector and the new vector can be expressed in this way. This is a rather geometric construction, and you see what I have done over here is that what I can show you now is that in this example, you can see there is a rotation of alpha. So the x and y components, of the vector originally A, this one, and the rotated one A prime, can be expressed as this: ax equal to a cos theta, which can be further defined as this: a prime x equal to a prime cos theta prime, which is the rotated one. And similarly ay which will be equal to a sin theta, which will be again in the rotated frame, will be a prime y equal to a prime sin theta phi. Now here is something important. You note this alpha, which is, I know it is a little bit hazy, apologies for that. This alpha is actually, if I zoom it, you will see it is a combination of this theta phi is basically a combination of alpha plus theta. Why? Because theta phi is the rotated one. So it is taking two angles. One is the original alpha plus the original theta. Now if I take this one, so this can be written as this one. Okay, so I just solve it and put the values which I have done. Cos alpha cos theta minus sin alpha sin theta. Similarly, a prime y can be written as this, as sin theta cos sin alpha cos theta and cos alpha sin theta. So this is clear. Now you see what we have done is that we have rotated this one. We have rotated the axis. Now the question comes here that before we go ahead, we need to know what is called a rotation matrix. Right, what is called basically a notation. Now this thing we can do it in a formula. I am not going to derive that formula, but I am going to show you the formula. But before that, a few quick basics on what is a rotation matrix, because otherwise you won't be, those you know, you can skip this part, but rotation matrix is something very important. So quick idea in what is a rotation matrix coming up in the next part of our video. So this is again a plain English definition. A rotation matrix is basically nothing but a transformation matrix which uses the general Euclidean space. So you see that in 2 dimensions, every rotation matrix will have a form of this. R theta is equal to cos theta sin theta minus sin theta cos theta. This is very plain and simple. Now if I call the rotation of the column vector by means of matrix multiplication will result into this. Now the coordinates, if I consider as x prime y prime, I mean to say the rotated one of the point xy, which is the original point, the rotation will result into this. X prime is equal to x cos theta minus y sin theta, and the rotated y prime will be x sin theta minus y cos theta. This should plus y cos theta. Now you see this is actually a very detailed derivation of the above formula, which I am avoiding just to keep it in I mean to say in the point. Now if I take a kind of a, what I would say, the rotation matrix, which is the 2-dimension rotation matrix, R 90 degrees actually looks something like this, which is these are just common rotation matrix, counterclockwise direction. R 180 would look like this, which is either in either direction a half turn, and R 270 degrees would looks like this, which is a counterclockwise direction. So this is nothing, just to give you that what it is and what all these things are all about. So let us go back to what we have left. So here you see that x prime is equal to x cos theta minus y sin theta, and y prime is equal to x sin theta plus y cos theta. So what happens is that this would lead to this one. Okay, a prime x equal to ax cos alpha minus ay sin alpha, and a prime y will be ax sin alpha plus ay cos alpha. Now we can represent this also in a matrix notation, which is simple like this. A prime x is equal to cos alpha minus sin alpha, and a prime y would be what? Sin alpha cos alpha ax ay. Now this actually gives you the tool or the idea that we can now find the components of a prime x and a prime y, which is what? Of the new vector, this one, a prime. So now what we get is that we are in a situation that we can now derive the components of this one, a prime x and a prime y, of the new vector a prime, which is in the original coordinate system. This is what we are actually going to do. Now in order to do that, we are trying to find out the components of the origin of the new vector, which is the a prime, in the original coordinate system. So how do we do that? It's very simple. I have taken these 2 diagrams, but what I am going to do is that I am going to rotate this alpha, this angle, to 150 degrees, a little bit more. So if I take the original vector as this one, this is the original vector, axi plus ayj equals to 5i plus 3j. If you remember in the last previous video also, I have taken the same values, and you will see how beautiful it looks like. Then what we will get is this one. Cos 150 minus sin 150, sin 150, cos 150, 5 and 3, it would give to minus 5.83 and 0.17. So what you see is that this means actually that rotating a vector through rotating this vector, original vector, through 150 degrees, actually this one, if I rotate this, so this is the original one, what I get is this one. So that means the new vector a prime is minus 5.83i minus 0.10 j. So this means that by rotating the vector a through 150 degrees, we have actually produced a new vector that almost entirely lies on the negative part of x-axis. Why? Because the value is negative. That means, let me explain it again to you. So if I take this one and with the original vector, if I get this, then this one, that is the original vector a, it gives the value of minus 5.83i minus 0.10 j. If I plug in the values of sine 150 degrees, which you can easily do. So that means that by rotating the vector a, the original vector, remember 150 degrees, we have actually produced a new vector which is entirely lying on the negative x-axis. So you can see that the noting that the x component is negative is larger compared to the y component. So remember that this is a new vector which is expressed on the same basis I and j, and it is not the same vector expressed on a new basis because we have rotated the vector on the coordinate systems. Yes, here it is. Remember that this is the new vector which is expressed using a new basis. Why? Because in this case we rotated the vector, not the coordinate system. This is important. So we rotated the vector only, not the coordinate system. Now if I go to the next page, question comes is that can we rotate the basis vectors using the same approach? Or I can more lucidly say that can we express the basis vectors of the rotated system in terms of the basis vectors of the non-rotated system? So if you're confused, look into this. This part is important because here the vector expressed using the same basis, and it is not the same vector. It is a new vector because here we have rotated the vector, not the coordinate system. But here what I am trying to do is that can we express the basis vector of the rotated system in terms of the basis vector of the non-rotated system? The answer is obviously yes. And here it is. If I take a unit vector I and if I rotate it at 150 degrees counterclockwise, then what we get is this one. I prime x, I hat prime x and I hat prime y will be equal to this 1 0, and it will again give the same value minus 0.866 and 0.5. Here what happens is that this I prime x represents the x component of the 150 degree rotated I vector, and I prime y represents the y component of the rotated I hat vector, and so on, right? And now also we can rotate j again in the same way, in the same counterclockwise 150 degrees, and what we will get is this, right? Now I will like to explain this in the next page. So you see j prime x and j prime y, again the values have swapped. 1 0 has become 0 1, so this has become minus 0.5 and minus 0.866. Here again j prime x represents the x component of the 150 degree j vector, and j prime y represents the y component of the rotated j vector. So now you see that this can be, if I wish to transform a set of basis vectors into new basis vectors, right, and we can use something which is called a direct or active transformation. So what we can say is that new basis vectors is equals to direct transformation matrix multiplied by original basis vectors. This is a kind of a, I would say, an easy way out. Now question is that can we see this in a diagram? Definitely. Let us look in the next part of our video. So here you see this one I hat. This shows y component of I hat in the original coordinate system and x component of I hat in the original coordinate system because I have taken the I hat. This one, if I take the j, it shows the x component of j in the original j system, and this shows the y component of the j hat in the original coordinate system. Now I would like to conclude the video with a very important observation, and this observation is coming with a comparison of certain important factors between the I would say first video, I mean to say sequentially second, and this video. So this is a very important observation. I would request to pay a little bit of more attention. So you see here, when I have done this part, that is components of the same vector equal to inverse transformation multiplied by components of the original vector, what I was saying is this: components of the original unit vectors which are in the non-rotated system is expressed in the rotated system. So original vectors in the non-rotated expressed in the rotated coordinate system. But when I do this one, what I'm telling is this: we are trying to find the components of the new vector in the original coordinate system. Mathematically, we can represent as this. If you go to my second video, you will see that I have done this calculation, and essentially what it tells is that it expresses the original vectors A, which is actually in the non-rotated system, and it is expressed in the rotated coordinate axis. So to summarize, we tell that it is from non-rotated to rotated. But in this video, what I have done is this, and this tells that the basis vectors of the rotated system in terms of the basis vectors of the original non-rotated system. So it's exactly the opposite, and here we say it goes from rotated to non-rotated. So the earlier video was basically the original unit vectors from the non-rotated to rotated. So non-rotated to rotated. Here we have expressed the basis vectors, I would say, in the rotated system in terms of the basis vectors of the non-rotated system. And you see beautifully these values are all the same. So this is a very important observation, that how we are going ahead. So here is a quick summary what we have learned today. What is a basis vector? How do we represent a basis vector? What is linear dependent and independent? How do we create a new vector out of rotation? And before that we have learned what is a rotational matrix, and non-rotated to rotated, and from rotated coordinate system to non-rotated coordinate system. In the next video, I would be talking about this basis vector and component transformation, non-orthogonal and orthogonal system, and then we will go ahead and find the covariant and contravariant components. So I would like to thank you immensely for taking out time and watching this video. If you liked my video, hit on the subscribe button and click on the bell icon to get all the notification from Physics for Students. This is my email ID, and this is my other channel where I am trying to put up some more videos on general theory of relativity. You can follow me on my Facebook, LinkedIn, Instagram and Twitter account. So that's it for today's video, but Physics for Students will continue on tensor analysis so on in the near future, and I will be very quickly coming up with other parts of the tensor analysis as well as with other videos. Thank you very much for watching this video, and please put up your comments and let me know how this series is going. See you soon, but till then, may the good Lord be with you.